Hey there students, this is the final video on exponential functions for the time being. I'm not on location this time, I'm simply broadcasting from the maths office on this occasion. Today we're going to be solving a tricky problem using a bit of technology, our class pad, and during our class time what we're going to be doing is having a look at some of the more nuanced ways that we can use the class pad to help us out in different scenarios. Before we do this question, we just got to remind ourselves of a quick something. So if we've got an exponential function f of x equals a to the power x, what do we expect that to look like when our value for a is greater than 1 or when it is between 0 and 1? So two pretty basic looking functions here. Let's have a look at this one. So f of x equals 2 to the power x. There's the big reveal. So what we've got there, we've got an a value of 2, which mathematicians have decided is greater than 1. So what we see in any situation where a is greater than 1 is that the graph is going to increase from left to right. So in each of those scenarios, whether it's 2 to the power x, 4 to the power x, 50 to the power x, 1.5 to the power x, whatever, as long as it's greater than 1, we're going to see a growth situation happening. Now, conversely, if we've got an a value that's between 0 and 1, for example, a half, we're going to see the graph decrease from left to right. And that's going to give us more of a decay sort of situation to deal with. So it's something to keep in mind where if you're talking about population growth or cell growth or something like that, we always want to make sure we do that mental check and make sure our a value is greater than 1. But if it's talking about population decrease, decay, something along those lines, maybe half-life in a physics context, we want to make sure our value for a is somewhere between 0 and 1. It could be a quarter, an eighth, 2/3, whatever. Right, so let's take that knowledge and apply it to a specific question. Okay, this is a kangaroo problem. There are approximately 10 times as many red kangaroos as grey kangaroos in a certain area. So the population of grey kangaroos increases at the rate of 11% per annum, while that of the red kangaroos decreases at 5% per annum. Find how many years must elapse before the proportions are reversed, assuming the same rates continue to apply. Righto. Okay, there's a lot of information in this question, so maybe let's break it down a line at a time. The one thing that I did write in advance is this: let G0 equal the initial grey population, just because I didn't think you'd enjoy watching me write all of that on the screen in real time. So let's go through and get all the information that we can. So there are approximately 10 times red kangaroos as there are grey kangaroos in a certain area. Okay. So let's have a look at that. So what that means is if we're going to represent that mathematically, it means that if we were looking at the number of red kangaroos and compared it with the number of grey kangaroos, if there's 10 times as many red ones, it means that we'd need to times the grey population by 10 to get the number of red kangaroos. So it's got like that sort of inverse quality to it. So that's piece of information number 1. Now we've got if the population of grey kangaroos increases at a rate of 11% per annum. Okay, let's do something with just that bit of information. So the number of grey kangaroos at a particular point is going to be equal to the initial number that we start with. And if it's increasing at a rate of 11% per annum, that's where we think, okay, our a value has got to be greater than 1. So let's multiply it by 1. But it's not greater than 1 yet. That's why I'm going to add on my 0.11, which is going to account for that 11% increase. We'll raise that to the power n for the number of years that pass as well. So that's our grey kangaroos. Then for our red kangaroos, their population decreases at a rate of 5% per annum. So let's come up with an equation for that. Your red kangaroo population is going to be, well, let's have a look at the information that we've got. So we know that at the moment, their current population is going to be 10 times the number of grey kangaroos that we started with. So 10 times GO. So that's what we're starting with. but it's now going to decrease at a rate of 5% per annum. So now we think and go, if it's decreasing, we need a value for a that's less than 1. So let's multiply that by 0.95, aka 100%, take away 5%. So if we multiply something by 0.95, we'll be finding 95% of it. And we'll raise that to the power n. Then what we want to do is have a look at how we're going to actually answer the question, or what we have to do. We've got to find out how many years must elapse before the proportions are reversed. So that's the last little bit of information. It's going to be that the number of grey kangaroos is 10 times the number of red kangaroos when the proportions are reversed. See, it is boring to watch me write on the screen. This is why I wrote the thing before. Anyway, let's keep going. Now, we've got a stack of variables here. So what we want to do is write this in such a way. So we want g to equal 10 times r, but we want to use just the one variable or see if we can use a couple of different things that we can cancel off to leave us with one thing to solve for. Because if we're looking for the number of years that need to elapse, we're just solving for n. That's the thing that we want to figure out. So let's do this. Let's take this proportion that the question needs. So we want the grey kangaroo population to equal 10 times the red kangaroo population. So let's rewrite our grey kangaroo population using this equation that we came up with up here. So let's say that g is going to be equal to g0 times 1.11 to the power n. Now what we want to do is sub in a value or an equation rather, for our red kangaroos, which we have up here. That's going to be 10 times the initial population of the grey kangaroos times 0.95. So now we're going to have the 10 from this expression here times our expression for the red kangaroos. So 10 times g0 again times 0.95 to the power n. Okay, so what we've done there, we've still got our n in there as an unknown, the thing that we're going to solve for. But the neat thing that we've done there is that we've got that initial population on both sides of the equal sign. So if I divided both sides by g to the power 0, because every term is being multiplied, if I just divide it through, I can cancel both of those off. And what it's going to leave me with on the left is 1.11 to the power n equals 10 times 10, which is 100, times 0.95 to the power n. Quick little rearrange of that. 1.11 to the power n over 0.95 to the power n is equal to 100. And just to reduce the amount of times I have to put a variable into my class pad, I'm going to use my index laws to pull out that to the power n. Because it's being applied to the numerator and the denominator, I'll just apply it to the whole bracket instead. And all of that is equal to 100. Okay, now time to get your classes paddus available. And let's pop that one in there. So we are going to hit action, we're going to hit advanced, we're going to hit solve, and now we're going to tell the class pad what we want it to solve it for. So I want to do 1.11 over 0.95, and I want to raise that to the power x. I know it says n here, but it's convenient for us to use x on the class pad, so that's what I'll be doing. And that is equal to 100. And I want to solve that for x, obviously. Let's hit enter. Okay, so you're not year 12 method students at the moment, so we're not doing logarithms just yet. So if you get an answer like this one, that's giving us the answer as like an exact value using logs. So what we want to do instead is change standard to decimal and hit enter a second time. And that has given us something that is not right. Oh! If you caught my mistake, well done. I did 0.05 instead of 0.95. Let's just make that correction. Good one. Okay, so that's spitting out an answer of 29.58. Let's go with n is equal to 29.6 years to one decimal place. Let's just check the question and see if it wants us to do any particular units or months and years or whatever. So it says how many years must elapse. So I think we're pretty good to leave our answer as that one. Okay, cool. And what you also want to make sure you add on there is if you've used your calculator in a particular way to solve a problem, you want to indicate on there what you've actually done. So I'm going to write CAS solve, as in computer algebraic system, I think it stands for. That could be wrong. But you want to say how you've actually used your ClassPad to work out the question. You can't just say ClassPad or CAS, you've got to use the actual function that you use. So in this case, we're using the solve functionality of the ClassPad. If you'd use gsolve or something like that from the graphing window, make sure you put in there the specific way in which you actually use that information. Might seem obvious that you've used your ClassPad to solve, but it's important from a working point of view that you include that information as well. Okay, good one. So during class time, we'll be using our ClassPads to find equations to fit different functions. So see you then.